Hello everybody, my name is Niek. I'm here to talk about glitching the TV streamer. We start off, can everybody hear me by the way if I talk like this? That's fine, because I don't hear myself. Alright, introduction, we're going to talk about the target. We're going to talk about the reconnaissance that we did on the target before we did the fault injection attack. We're going to talk about the fault injection attack itself and some takeaways to wrap up the slides. I'm Niek. I'm from the Netherlands. I work for a company called Reconnaissance, which we started 5 years ago, where we do device security. I'm a researcher / trainer / consultant, but some of the things you probably have heard of about is the trainings that we do. For example, this conference, we gave 2 trainings, one on secure boot and the other one on fault injection, but we also have a training on execution environments. And these trainings are typically flowing from the research that we're doing. Most of our research is actually written down on our website in a blog, so if you're interested in some of the other things that we did, feel free to go there. But today we're going to talk about something that's not there yet. Eventually it will be written down there. So let's start with the target. So the target that we chose for this particular research is made by Google. It's the Google TV streamer. As the name already states, it's used for streaming stuff to your TV. It's not very surprising. Whenever you start analyzing this device from the outside, you'll see that it has a bunch of interfaces. Not a lot actually. So they're all on the same side. So there's an LED, there's a button, there's a USB connection, there's Ethernet, and there's an HDMI. So you can already imagine what those things are for, of course. And of course it's also, we can assume that there's some Wi-Fi connectivity, right? So we don't need to use cables in order to communicate with it. Once you open it, you're presented with a fairly complex device with a bunch of components, but the functionality is all done by separated chips. There's a system on chip, which is of course the heart of the device, which communicates with the DDR chip in order to have volatile memory available for the software. There's an Ethernet chip to provide Ethernet connectivity. And there's a separate chip for providing Wi-Fi. So this is external to the SoC. On the other side of the PCB, there's an eMMC, which is also external to the SoC. There's another SoC for another type of Wi-Fi connectivity. So for Zigbee, Thread, low power Bluetooth. And there's a PMIC providing power to the various places on the PCB, the chips that they need. So the CPU inside the SoC is actually, the base frequency is 1.8 gigahertz. I think it can be clocked up to 2.1. And it's a quad-core CPU. Keep that in mind, because that is the actual target of this research. So simplified diagram a bit of what is happening on the PCB. So there's the SoC, which is able to interface with the various chips on the PCB as well. So there's a DDR bus towards the DDR, there's an MMC bus towards the eMMC, and there's some connections to the Ethernet chip and the PMIC. In the picture, we do not talk about the other chips that were previously mentioned, but they of course have, also connections to the SoC. So how can we attack this device? Well, as you probably all realize, there's numerous ways of doing that, but because we're at hardwear.io, let's stick to what hardwear.io is about. As we say in Dutch, u vraagt wij draaien. So that basically means let's do something related to hardware attacks, right? Because that's what we are probably most interested in. So let's slowly build towards that. If you start analyzing the security of a device, you always need to do some form of reconnaissance in order to learn a bit more about the device. So that also means that even though you're planning to do a hardware attack, you need to analyze the software too. So one of the first things we want is to get access to whatever is running on the device. So let's look at a few standard things first in order to get access to that. So usually there's a serial interface. Well, we looked for it a bit. We did not really find it. So we know this device is also part of the hardPON. So I'm not sure if there's anyone here that already looked at the device and found the serial interface. Please let me know, because I will be curious to hear about it. We are not using a serial interface in this research. Then the next thing you're typically looking for is to dump the flashes in order to get access to whatever is running on the device. We did not do it yet. I mean, we probably should, and we're probably gonna do this, and probably it's not that difficult because it's an eMMC chip, so you can use the 1-bit mode in order to get access to the chip contents while it's still being soldered onto the PCB. Similar fashion what we showed last year, where we did this for another Google product, the Wi-Fi Pro. But for this research, we did not go that route yet. We will probably do it, but we haven't done so far. This device actually is very similar to a phone at the functional level. I don't mean you can call with it, but at least it runs Android and a fairly recent version of it. So there's also ADB, which we can enable in a very similar fashion. So we can, using the remote, we click the build number a bunch of times, enable developer options, and we can enable USB debugging. So then when you put the USB cable inside your computer instead of your power adapter, it will be exposed to ADB and we can interface with it exactly like on a phone. So let's explore a little bit what we can do. So we can get some info, so we can see the properties that are set in Android in order to determine if certain security features are enabled, or maybe SELinux is in permissive mode. And we can, of course, read the firmware versions. It can be useful. We can get the kernel configuration, which is useful because then we have an idea to what extent kernel hardening features are enabled in Linux. This can be useful if you, for example, aiming to escalate privileges outside of the ADB shell, for which you probably need to attack the kernel. So that's useful. And we can run custom code. So this is not typically something that is always available, let's say, on other embedded devices. For example, on the Wi-Fi Pro, also made by Google, even though it is also a bit of overlap with Android, this was not possible. So we were not able to run custom code there. But on this device we can. But you can actually do this on any Android phone. It's just how Android works. So we can just write some code. We use the Android Studio in order to compile it, and we can just run all sorts of stuff in the Android user space, of course, in an unprivileged context. And this unprivileged context is the reason that we also cannot do a lot of things. So for example, we cannot read most files. We cannot even read the kernel log. And we also cannot read the flash. So even though we can run custom code or arbitrary code, we cannot do a lot of things with it. And the reason for that is the UID sandbox. So this is provided by Linux. So that means that an unprivileged user cannot read other people's files. So we cannot read the files from root, for example. And on top of that, there's another sandbox, which is the SELinux sandbox, which is also in place. So even if we would bypass the UID sandbox, SELinux sandbox may still have some restrictions for us. But this is basically how it works on a mobile phone as well. It's exactly the same. So in order to understand more, we need something to reverse. So we either need to dump the flash, or we need to go another route. So we decided to look into how firmware updates are being done. And they're actually being done very similar fashion as on the phone. They're just provided to the phone whenever needed. There's not a file you can download. There's not something you can provide to the device. The device is responsible for updating itself, just like your Android phone. However, as you may know, you can actually download these OTA updates yourself, as long as you know how to interface with the Google servers. So that's exactly what we did. And once you interface in the right manner, and you tell to the Google service, hey, I'm a streamer, you get a link back. And from that link, you can download the update. Very similar as on the phone. So this gives us at least something. So we started analyzing this update. We figured out that some already made tooling for this update to unpack it. And once you unpack it, you're actually presented with all the partitions that are flashed to the eMMC whenever the firmware update is being done at the device level. We analyzed the partitions a little bit. We will not discuss them in utmost detail, but just take away that some of them are encrypted and some of them are not. For example, boot IMG, which contains the Linux kernel, or the Android kernel, I mean, and for example, system, those are not encrypted. So whatever is in there, we can get access to. And because we are aiming to escalate privileges in ADB, or from the ADB shell, later on, we decided to analyze the kernel in more detail in order to understand what it's doing to prevent us from escalating privileges. But after a while, after spending a bunch of hours, we actually realized something. This thing is just running the generic kernel image, which you can just download. And even more than that, Google provides the exact one-to-one binary, because you see that the SHA-1 hashes match with the kernel we obtained from the device and from the Google website. But it actually also provides debug builds and all the artifacts that are created at build time. So it also provides us actually a VM Linux file, which is an unpacked kernel with all the symbols inside. And moreover, the source code is simply available. So basically we have everything. Binary with symbols and source code. Makes our lives a little bit easier, because then we know what to reverse. or at least it's easier to reverse. So there's a few other things that restrict us. So there's typical security features that you find on embedded devices and on phones. So there is secure boot. So this typically refers to, at least in the context of Android, to whatever the SOC manufacturer provides in order to make sure that the software that's running on the device is authentic. So this starts from the ROM and flows down to the Linux kernel, and then Android verified boot takes over to make sure that also some of the user space code is genuine, so you cannot tamper with it. Very similar as on the phone. There's Android kernel hardening, there's a trusted execution environment. And actually the security posture of this device is similar to a Pixel 9. I have the Pixel 9 here, so that's what I compared it to. It's fairly similar. So also the kernel hardening for this device is very similar to a Pixel 9. I didn't see major differences between that. Probably just the standard Android kernel configuration that they provide. One big difference, of course, between this device and a Pixel phone is the fact that this device does not have an external security chip like a modern Pixel phone will have. So the Titan security chip is not present. So that means that most, let's say most relevant assets are probably protected by the trusted execution environment only. Basically what was happening before we had external security chips on mobile phones. Maybe 5 years ago, something along those lines. So, how do we get in with something physical? Well, we like fault injection, so that's typically one of the first things we look for. There's quite a few fault injection attacks. I suspect they all, to a certain degree, give an introduction to fault injection, but let's go over it very quickly again from our perspective. So, we are using a glitch to alter the intended behavior of hardware. So that also means that whenever we inject a glitch, we are actually triggering a hardware vulnerability. Fault injection vulnerabilities got nothing to do with software. It's hardware that makes mistakes when we inject those glitches. But if we target with this glitch a CPU, we are corrupting instructions that are being executed. So by triggering a hardware vulnerability, we have an impact on the software that's being executed. As a result, any software security model that is implemented in the device and that the device relies on will just simply crumble away. Because whenever instructions are not being executed correctly anymore, then that software security model will simply not work as intended, hence it can be broken. In this case we used EMFI, so that means we are generating an electromagnetic glitch in order to make the circuit inside the chip do something else than intended. And this works by generating a high current through a coil in order to generate this electromagnetic field. One nice thing about this electromagnetic field is that it has a localized aspect to it. So that means we need to place this probe on different locations on the chip surface in order to find sensitive locations where we can inject this glitch in such a way that we can affect the CPU while it is executing instructions without affecting the continuation. We only want to affect one or a few instructions at a very specific moment in time, but after that everything should commence or continue as intended, because then we can, for example, bypass a check or change a configuration option. And this technique we have been using throughout the last decade on a wide variety of chips, small, big and bigger, slow and faster, and it always worked. If there's nothing specifically implemented to make these attacks more difficult to perform, so-called fault injection countermeasures, this will be possible on a standard architecture. And this includes most ARM chips, but also other architectures as well. Even if they run at 1.8 GHz. Keep that in mind. So this is the setup that we use. There's not a lot of fancy things going on. Later on you realize why. Normally hardware hacking is a lot of wires, right? We used no wires, no extras. We only needed a few things. So this is the full setup. So we placed the board fixated in the XYZ stage. XYZ stage is very similar to a 3D printer. So you can move the device across the chip surface. So that allows us to move the coil. Later on there's a picture of the coil itself. Then we use a device made by Keysight that allows us to control when we inject the glitch and how strong this glitch will be. So basically how much current we will drive through this coil. Because the communication and the power is provided via the USB interface, we use an additional device that allows us to turn on and off the USB connection. And we use this to reset the target, because when we inject those glitches, it is likely the device enters an error state, and this allows us to get out of that state and get it into a good state again in order to try our glitch. These type of attacks, it's impossible to get it immediately right. You need to inject many glitches at many different moments in time at various locations in order to find that location and moment in time where you can be successful. So inevitably, you're gonna reset that target a lot of times. So you need a good reset or a good way for resetting the device in a known state. In this case, this was the USB connection itself to power cycle the device. So this is the probe that comes out of a bigger box. So it's maybe a bit difficult to see, but at the bottom of that little black thing, you see a small red wire. That is the actual coil that emits the electromagnetic field in the chip surface. Please note, if you're interested in seeing this better, there's a demo of doing exactly this at the Keysight booth, at the, I guess, commercial hall, whatever you call it. Please go there. I will be there. And if you don't find me, there's other people there that can discuss exactly what it's doing. At the moment, it's scanning the chip surface in order to find sensitive locations. Tomorrow we will inject glitches to get a root shell. So there you have an idea what's going on. So what can we achieve? So this is just an example. For example, these are 5 ARM64 instructions which are used to increase a counter from 0 to 4 using a sled of add instructions. When you assemble those, you get hex values, and of course, when you take the binary of that, you get the zeros and ones that everybody's always talking about what computers do. So each instruction is encoded in a specific manner to define what the opcode and the operands are. So after these 5 instructions have finished executing, X1, which is a register in ARM, is set to 4. This is the intended execution. Whenever you start injecting a glitch while those instructions are being executed, we can do the following. We can change 1 bit from 1 to 0 in the instructions encoding, which of course is reflected in the hexadecimal representation. As you can see, 21 is glitched into 20. 1 bit went to 0. And this has an impact on the instruction which eventually is executed by the CPU. In this case, one of the operands got changed. So now the destination operand instead of X1 is X0. And a side effect of that is that after these instructions have been executed, X1 is not 4 anymore, it is now 3. Because that add instruction is still executed, but with different operands. Similar fashion, we can also flip a bit somewhere else in the instruction. So now in the beginning it is flipped, a bit difficult to see, but in the hexadecimal representation it's easier to see. We see that 91 is flipped to 90, again 1 bit difference. But now the operand is not different, the actual instruction itself is different. So the instruction is not skipped, it is actually corrupted in another instruction, valid instruction, which is completely different than an add instruction. So if you're familiar with these assembly instructions, this is an instruction that gets a relative offset from PC. I don't know what PC is now set to. It's not 5. But it will likely be a large number, resulting in X1 being actually something big as well. Now you can imagine, the streamer will not be running these counters, right? They will be using instructions to do a lot of things that are important for the user, watch Netflix or whatever. But it will also use these instructions for some security sensitive operations. And if you can affect these instructions, that does also means that we can affect those security sensitive operations, eventually leading to a successful attack. So what can we attack? Well, the most typical thing to do on an embedded device with fault injection is bypassing secure boot. So most public examples are about exactly that, bypassing secure boot. The reason for this is that it's not always that easy to break the secure boot implementation on some devices. And secure boot of fault injection is actually more, with fault injection you can even try this without having access to software vulnerability. So the idea there is that you inject a glitch in order to, for example, bypass the signature verification, and that allows you to execute an unsigned bootloader. From that point on, you have an entry point in the device, you can run custom code at a high privilege level, after which you can get access to some of the firmware or binary software that you're interested in order to find software vulnerabilities. But this is your initial way in. This is, for example, also how some of the consoles are initially broken, after which more impactful software vulnerabilities are found. But this is the initial entry point to understand the device better. We can also break into the debug interfaces, for example, recovery modes that are implemented on phones or other devices in order to get an initial foothold in the device, after which we can analyze the device further. We can escalate privileges, for example, from user to kernel, or from the re to the t, which is something we demonstrated last year on the Wi-Fi Pro. But of course, there's a wide variety of attacks. Please note, these are examples of attacking software that's running. You can also do attacks on hardware, pure hardware implementations, but we will not cover them in this talk. We decided to actually take the ADB shell as a start and go from there. This is not a new idea. About 10 years ago, we had a paper where we explained how we escalated privileges in Linux from user to root, from user to kernel. So we got PC control over the kernel. And we decided to do something similar, but then on this device in Android. And because Android is very similar to Linux, we did not expect any issues there. So let's first figure out if the CPU is vulnerable. So there is ideally a phase before the attack where we determine if the chip is vulnerable or not. In this case, we run custom code that's trivial to glitch on the device. We're actually using code that's very similar as the counter we just looked at. We just extend the counter a little bit in order to make it the duration longer, but we'll look at the code later. Please note that normally you would set a trigger just before this code that you're running. And you will get a response from this code directly when it has run. Because then the idea is you inject a glitch. If the response is differently than expected, you successfully affected the CPU. In this case, we're restricted in the ADB shell. We cannot set the GPO signal. And also we decided not to have a direct response. So we're basically running triggerless. Later on, it will clarify a bit more. The idea here is that at this point we don't know what locations on the chip are vulnerable, so we need to find those locations. So we need to scan the chip service with this custom code in order to find those locations. And then we want to determine what kinds of faults are applicable. For example, instruction corruption, like we already discussed, instruction skipping. Even though the instruction is not skipped, behaviorally it can still be a skip, right? Because if we change the add instruction to something else, without any side effect other than not executing the original instruction, behaviorally it's like skipping an instruction. But it can be data corruption as well, and a fault model is just a description of a fault, so there will be other descriptions possible as well. And then the idea is, from this characterization phase, we use the information that we obtained for an actual attack. So this is the code itself. Please note that this is running in user space in a while loop, so this is constantly executing, and we run this in the background. So it is just using an add instruction to increase a counter from 0 to 10,000, 2710 in hexadecimal value, and then this counter value is not being sent back to us. It will simply check itself if the counter was 10,000 or not, and whenever it is not 10,000, it will actually write the different counter value back to disk. And that's what we use as a classifier to see if we're successful or not. We don't get the response, we simply check if this file is present or not. If the file is not present, we were not successful. If the file is present, we were. Keep that in mind. So this is roughly the flow. So we start, we reset the streamer, we run the process with custom code in the background, we inject the glitch, and we check if the file is there. If the file is not there, we glitch again. If the file is not there, we glitch again. So there's no delay, no trigger, nothing. We just keep glitching until we see a successful fault, or we get an error. For example, a timeout on ADB, or a timeout on the device itself. And at that moment, we reset the streamer into a known state, and we try again. In order to find the locations on the chip efficiently, we have a two-phased approach. So first, we scan the entire chip. For each location, we increase the power of the probe very quickly. So we go, let's say we have a range from 1 to 100, we go 10, 20, 30, up to 100. So 10 glitches at each location. If we do not find any alteration of the intended behavior, whether that's a successful fault or a timeout or whatever, we discard the location. Whenever we do find an alteration of the intended behavior, we add the location to a list. And then in the second cycle, after we scan the entire chip, which takes about 40 minutes, we only scan the locations, or we only test the locations where we found the glitch had an impact. This includes, of course, also locations where we cannot have a successful fault, but it definitely also includes locations where we can have a successful fault. So this allows us in a couple hours time to scan the entire surface of the chip and give us some locations where we potentially can perform an attack. This is exactly what's running now at the booth, at the Keysight booth. So this is the initial scan. It's maybe a bit difficult to see. Later on we see a better picture, but this is the grid that we used for scanning the chip surface. So this is the same dimensions as the chip, just a bit bigger. The points are a bit at different locations because we add a little bit of noise so that the points are not plotted on top of each other. But this is a 20 by 20 grid. These are just the locations from the second phase. So this is all the locations where we see alterations of the chip based on the injected glitch. And as you can see, it really matters where you place this probe on the chip surface to what behavior you see. And this is the same locations, but then only the locations where we were able to successfully change the expected counter. And as you can see at the bottom, there's like a thicker blob. So we were successful more times than at the other locations. We don't know if we affect the same parts of the system or the same parts of the CPU. We have not analyzed the data yet at this point, but at least it shows that one location seems to be more efficient than others. Still to find out. So to give you an idea what kind of responses we get back, we can get an expected response. So basically 2710 means the counter did not change. ADB timeout, device timeout. And these are just some examples that we got in that particular run. We get 270F, which basically means the counter is counter -1. So for some reason, one of the add instructions did not execute as intended. We get 270E, which may mean 2 instructions are not executed as intended. We get 270C, which is counter -4. Maybe 4 add instructions are not executed as intended. At this point, these are just guesses, right? We do not have enough insights into seeing exactly what goes wrong. We can just behaviorally see what is going wrong. But from an attacker point of view, this is already sufficient. And one thing we're also often looking for, if we see any weird values that are maybe coming from the CPU state itself. So in this case, we got an address which probably relates to a memory address, which is hopefully shifted from another register into the register that's used for the counter. This gives us some confidence that what we are seeing is actually instruction corruption. And this is what we're looking for. Because instruction corruption is the most powerful fault model that exists. We can change any instruction into any other instruction. Just the chances of flipping specific bits, the likelihood for doing so is of course different. One other thing we did, there was side quest. The chip is a quad core, so we decided to run the test code on the different cores. So whenever we run the code on the core 1, on core 2, on core 3, and core 4, the sensitive locations where we can have a successful fault are different. Which makes sense because, of course, physically these cores are implemented at different locations inside the chip circuitry, right? So this matches with our, let's say, hypothesis that we are really affecting the CPU with the glitches we inject. Because there is a clear dependency on what core the code is running. So this is a good sign for us. We are glitching the CPU. From this point on, we just decided to go for that location which seems to work better. We fixed the probe there, and for the attack itself, we're not scanning the EM probe anymore. Because the scanning is a time-consuming operation, and we want to be as fast as possible. So we fixed the probe there, and we do all the testing that comes after on that particular location. So how do we get root? We issue the set UID syscall. This is the same one we used on Linux, in order to set the UID of the running process to root. So this syscall is a little bit more complex to that, but for you it's enough to take away that this allows you to set the UID to any other UID, as long as you have the privileges, of course, because otherwise the kernel says, yeah, fun that you want to set me to root, or you set yourself to root, but that's of course not allowed from a process that's running in the ADB shell. So this is exactly what we need to circumvent in order to get root with the glitch. So we have the kernel source, so this is a bit simplified, but if you ever looked at it, then this is roughly what you see. At the beginning, you see the arguments going into the syscall function. So these are the values that we provide. So we set it 3 times to 0. So these are the real ID, the effective UID, and the saved UID. What that exactly means, we can discuss offline, or you can look it up in the mem page. It's not important for now. The important part is that the capability check, and capabilities are basically in Linux determine what you can do as a process. That check is preventing us from doing that from the ADB shell. that check is the one that's failing. Later on in the syscall, there's also some hooks for Linux security modules. And in this case, there's only hooks for SafeSet ID and common cap. But luckily for us, they do not have an impact, because SafeSet ID is not available on this particular device, and maybe this is the same across Linux or across Android. I did not check. And also the common cap hook will not have an impact. So the only check that we are blocked by is the check on the cap set UID capability bit in our capabilities structure. And of course, this check we can potentially bypass using a glitch. So our attack code, very similar to characterization, we again run something in a loop in the background, but in this case we're constantly issuing a not an SMC, I'm too much thinking about T's, constantly issuing an SVC towards the Linux kernel. So that is how a Linux user space process can communicate with the Linux kernel in order to ask the kernel to do something for the process. So in this case you see R0, R1 and R2 are set to 0. These are the arguments that will be passed to the function we just looked before, and the 208 is the identifier for issuing a set UID syscall. SWI 0 just means we're going to do the context switch towards the Linux kernel, and then the other the move is basically moving the return value of the syscall back into a variable that we can read from C. Before, we were actually writing to a file whenever we saw the counter was different. In this case, we are creating a file whenever we get 0 back, which is an indication we bypass the check. And whenever we do so, we start simply telnet D. Because at that moment, if we are successful, the process is running as root. And whenever we spawn another process from this process, it will also be started as root. So then once telnet D is running, if we connect to it, we should be presented with a root shell. So the attack flow is a little bit different now. We reset the streamer, we start the process in the background, we inject the glitch. Again, no trigger, no delay, just glitching until we see something happening. If we get errors, we reset the streamer. If we do not see any effect, we keep glitching. But if we see a successful glitch, the process will simply start telnet D and it will stop. And also our glitching will stop. Because if we would continue glitching, we would break our root shell, right? At that point, we want to connect. So the glitch parameter search strategy in this case is fairly simple. It's just injecting glitches with random power. We don't do anything else. And of course, we set this power to the information we obtain from the characterization. Which in theory could be slightly different, because now we are attacking the kernel instead of a user space program. But we found them to be roughly similar. So this is a screenshot of our glitch. I don't have a demo here in States, unfortunately, but it's running at the Keysight demo, like I said. So here the 110, 111, 112, so it's, let's say, the 110th experiment, the 111th experiment. And the printing you see is basically an ls on the directory where we expect the file to be. And then for the 113 experiment, you can indeed see the success.txt is actually printed, which is an indication we were successful. And we, of course, stop the script, use telnet to connect to the device, and we are presented with the root shell, which we confirmed with the whoami command. You clap too soon. We have limitations. So, even though we are root, we are still restricted by SELinux. So, even though the root shell runs at root, the context did not change. That is done at a different level. So that also means that we can still not read flash. That is reflected here in the log cut. So we try to read the flash, and then SELinux will actually kick in. So there's a few files extra that we can read. But at the end of the day, the layer defense from Android actually worked in this case properly. So, bad news, we have not bypassed SELinux yet. We are working on that using a different method, but with this approach, this is not possible. So another thing we did, maybe interesting to share, other syscalls are of course protected in similar fashion. Even if we can glitch the protections from one syscall, we can probably do it for another. So the ADB shell, with that privilege level, you cannot read out the syslog. So one of the things we did a lot of other things, but this is one of the interesting ones to share, is that we are able to read out the syslog by injecting a glitch. So this allows us to bypass the check that you see there, check syslog permissions. which actually is a check both for the UID, or for the capabilities, and for SELinux, not SELinux, the Linux security modules, hooks. So we bypass in a similar fashion in order to read out the syslog. This is maybe not that useful. It prints some useful information, but at least it shows that we can bypass the checks that are done in the kernel, which gives some confidence that other attacks should be possible as well. So like I said, we're working on these things. Maybe we can share them next year, and maybe we do that somewhere else, if not here. So the takeaways. The Mediatek is SOC, and especially the CPU inside, because that's the one we in the end targeted, is vulnerable to EM glitches, which has a result that the software is not executed as intended, even when it runs well beyond 1 gigahertz. Fault attacks on Android at runtime can be effective, even when the overhead that you get for resetting the device all the time, because you need to wait for Android to be fully started, is significant. It's still possible to do it in a matter of I would say matter of minutes, and I mean anything up to 1 to an hour. People don't agree with that statement, but let's say in tens of minutes you have a root shell presented to you. However, we still think that attacks during boot are, of course, much more powerful and also usually more efficient to perform. Software security model of Android kernel fails when you start injecting glitches, which is not surprising because it's running on a vulnerable platform. And its layered defenses saves it, at least from us, for now. Because we have not demonstrated the full compromise of the device, we are still restricted by SELinux, and we likely need to have some form of a kernel right in order to get rid of the restrictions that SELinux imposed to us, or we need to perform an attack in a different manner. And we hopefully are able to share these different ways with you in the near future. There's a demo at the Keysight booth. We are running exactly this, what I showed. Nothing is a gimmick. It's really the Google device running, nothing else than the latest firmware version. So have a look there if you're interested. And other than that, thank you very much. And if there's any time for questions, I'm happy to answer them.
Thanks, Nick. Do we have questions in the audience? I know we have at least one question.
I have a question, real quick.
Yeah.
Why did you decide to attack the kernel, not the bootloader?
We wanted to show something different this time, and we think runtime attacks are not shown in public too often. It's on our list to go for the bootloader, definitely. Yeah.
Thank you.
Okay. Thank you very much for an amazing presentation. Have you contacted the manufacturer? And what was the reaction? Because I assume you did.
We shared the results with Google and with Mediatek. They're very interested. We discussed with them the results. However, they also indicated that they expected that these type of attacks are possible on this device, simply because the platform is not specifically hardened against these fault injection attacks. So this is not an issue specific for this device or this specific SOC. This is applicable to most SOCs. So it's definitely not, let's say, a mistake from either Google or Mediatek.
Okay, thank you. One more small question. Did you try anything like this, trying to modify registers, like link register or something like that? So like wild jump?
Yeah, you're referring to getting control of the program counter directly by providing... Yeah, no, we have not went that avenue yet, but that may actually be part of the things we are working on.
Thank you very much.
We have another question from here. I'm here.
So, thanks for the great talk. So, did you understood whether the instruction corruption was happening inside the data path or in the cache or in the SRAM where the code is being held? I mean, where it did happen?
Yeah, from past experiences, we typically say that probably the most sensitive part is whenever the CPU is fetching the instruction, because that goes over a bus. And then probably that is easier to influence than, for example, the decoding inside the CPU. But on this particular platform, we did not have a lot of, let's say, insights into what exactly was going wrong. So it's hard to say. Yeah.
All right. Any more questions to Nick? Yes.
Yeah, there was one set of slides that you showed the phase 1 and phase 2, and then you were highlighting points. And at some points, like I would imagine that each next picture would be a subset of the previous one, but I've seen like the area diverge from left to right on your picture. Maybe if you can elaborate.
You're talking about this?
Yes, exactly, this one.
Yeah.
So the sensitive locations on the left, but the successful are more on the right. Maybe if you can explain a bit more what's that about.
Sure. So all the results, what is shown in this picture, are also in the left side of the picture. But it's just filtered out. So it's indeed not exactly matching. But there's no slide there. So on the left, the initial scan is the entire surface of the chip, right? The middle one is just the locations where we glitch more. So it's, let's say, perspective is different. Yes. That makes it a bit confusing indeed. Yeah.
All right. Any last question to Niek?
I'll be around. So if there's anything coming up, feel free to pull my shirt. Thank you.
But don't pull too hard.